Hi, this is Miss Fitzmaurice, and this video is about universal gravitation. So by the end of this video, you should be able to explain to someone the difference between universal gravitation and the gravitation we've been using in class, Fg equals mg, and maybe even tell them why they're actually kind of the same. You should be able to use universal gravitation formula to calculate a gravitational force, and you should be able to combine universal gravitation with circular motion. Okay, so first of all, let's talk about gravitation in general and on the Earth. Okay, so on the Earth, or if you're pretty close to the Earth, you're just going to use the formula Fg equals mg. Okay, and you know, you've done this a bunch of times, that m is your mass, and g is 9.81 meters per second squared, and you'll actually even find a more precise value later on this year in a lab. Okay, in general, you saw this last night, universal gravitation equation, and this is for the Earth, this is for the Moon, this is for everything. The force of gravity is between two objects. It is capital G, which is a special number, I'll tell you, m1, m2 divided by r squared. Okay, so anytime you have two objects, no matter how big or how small they are, kind of like if you had two magnets, they attract each other. Okay, m1 is putting a force on m2 because of gravity. m2 is putting a force on m1 because of gravity. And how you find them is basically this equation. As you might guess, r is just the distance between them. m1 and m2 are the masses, and g is this horrible number, but you'll come to know and love it. It's equal to 6.67 times 10 to the negative minus 11. Okay, and the awful units associated with this are meters cubed times kilograms negative 1 times seconds negative 2. All right. So this is true universally. Okay, that's why we call it the universal gravitational equation. And in fact, it's also true on Earth. What you could do is you could take the mass of the Earth. Okay, so these are really the same formula. For the Earth, we have Fg equals the mass of, the person or whatever. And if we took G, capital G, 6.67 times 10 to the negative 11, times the mass of the Earth, and divided it by the radius of the Earth squared, you would actually get 9.81. Okay, so again, the equation we've been using is pretty true for close to the Earth's surface. This is what I like to think of as the real equation for gravity. It's always, always true. Okay, so we're going to do an example, and you are going to calculate the force between the Earth and the Sun. Okay, and I'm not just going to provide you with the numbers. You need to get used to being able to look numbers up. So you're going to calculate the force, but you need to find out some things. So you need to find the mass of the Earth, you need to find the mass of the Sun, and your distance, I'm going to say RES, the radius between the Earth and the Sun, is going to be the distance from the Sun to the Earth. Okay, so take a minute, look those things up, try to plug it into that monstrous equation, F equals G m1 m2 over r squared, and you will be able to calculate the force between the Earth and the Sun. All right, so now that you've done that for yourself, let's go over it. We have Fg, okay, it's still a gravitational force, is equal to capital G. The mass of the Earth is equal to 5.97 times 10 to the 24th kilograms. And the mass of the Sun is equal to 1.99 times 10 to the 30 kilograms. Okay, the distance between the Earth and the Sun, I mean, it varies a little bit as the seasons progress, but overall, on average, in meters, the distance between the Earth and the Sun is about 1.5 times 10 to the 11th meters. Okay, so Fg is G times m Earth, m Sun, divided by r squared. And if we put in all those awful numbers, we have 6.67 times 10 to the minus 11 times, I'm going to round, this is about 6 times 10 to the 24 times 2 times 10 to the 30, all divided by 1.5 times 10 to the 11th squared. I'm going to put that into my calculator, and I wind up with this force, which is about 3.5 times 10 to the 22nd newtons. All right, so that's a pretty big force, but if you think about it, it's acting over a distance of 93 million miles, or 1.5 times 10 to the 11th meters. It's kind of incredible. Okay, the next thing you're going to do is we're going to combine this with circular motion. Okay, and we're going to use that force we just found to ask how long is a year. And you might say, okay, how am I going to do that? But let's think about this. The Earth is going around in this circle around the Sun. It's not an exact circle, but let's, for guesstimation's sake, we're not getting that complicated just yet. Let's say that it's an exact circle. Okay. And let's say that the amount of time it takes to go around the circle is our period. Okay, we know that our period, that's a year, and that's equal to 2 pi r divided by v. Okay, basically what I did is I took v equals 2 pi r over t, which you saw in the last video, and I cross-multiplied. Okay, I also have the force between the Earth and the Sun. Okay, so what I can do is I know that Fg is equal to the mass of the Earth times v squared over r. And I know that v is 2 pi r over t. So I have Fg is equal to the mass of the Earth times 2 pi r over v, over t squared, all over r. I'm going to do a little bit of algebra, and I actually want you to try to pause this and solve for t, because t is the length of our year. Okay? So, now that you've tried to solve for t, you should realize we can cancel out one of our r's and the r down here. Okay, so that goes away. I'm going to get rid of this squared, and I'm going to put t squared, 2 squared, and pi squared. Okay, now I have Fg is equal to the mass of the Earth times 4 pi squared divided by t squared. I'm going to cross multiply. I have t squared equals me times 4 pi squared over Fg, and my final step is to take the square root. Okay, I want you to take the square root, and you end up with t is equal to 2 pi times the mass of the Earth divided by Fg. Okay, so what I want you to do now is take that Fg we got from before, so that was 3.5 times 10 to the 22 newtons, and put that in, and I want you to see how many seconds are in a year. Okay, so go ahead and plug that into t. We will talk about the answer in our next video.